I'm just going to come out and say it. Every time you see a GMAT problem that appears to have absolutely nothing to do with ratios, there's a 60% chance it's a ratio question. In this video, we're going to explore all the different ways in which they can disguise a ratio question and learn how to translate things that appear to have nothing to do with ratios into ratios. We're also going to learn how to use those ratios to our advantage and make seemingly very hard questions appear like a piece of cake. Let's take a look. All right, let's start with the somewhat more obvious. When the GMAT says there are two pumps filling a swimming pool and the fast pump is 3 times as fast as the slow pump. Well, that's a ratio of 3 to 1. We could say fast to slow is 3 to 1. And we could also say that together, how fast are they? Well, they have 4 ratio units of fastness. All right, so we would say that together they are 4 times as fast as the slow pump on its own. We could also say that together they are 4/3 as fast as the fast pump on its own. We could say that the fast pump is 3/4 as fast as they are together. We could say the slow pump is 1/4 as fast as they are together. We can take this further. We could say that together they'll take only 1/4 of the time that the slow pump would take on its own to fill the pool. We could similarly say that together they'll take 3/4 as much time as the fast pump would take on its own to fill the pool, and so on and so on. So we can see that ratios can be very, very useful. What if one of the pumps, let's say the fast pump is filling the pool and the slow pump is emptying the pool? So again, the fast pump is 3 times as fast as the slow pump, but this time there's a twist. The fast pump is filling the pool, the slow pump is emptying the pool. Overall, is the pool getting filled or is it getting emptied if both pumps are working together, working at the same time? Well, it's getting filled faster than it's emptying, so overall it's getting filled. How fast is it getting filled? Well, for every 3 ratio units coming in from the fast pump, 1 ratio unit is leaving from the slow pump. So the net effect on the pool is it's filling at a rate of 2 ratio unit, whatever that means. All right, let's keep going with this. What if you have 2 pumps filling a swimming pool, but this time the fast pump is 50% faster than the slow pump? Another way of saying that is the fast pump is 1.5 times as fast as the slow pump. Those mean the same thing. Well, again, we could build a ratio, and there are a couple of ways you could do this. So when something is 50% more than something else, you could use 150 and 100 as your numbers to build your ratio. I would suggest reducing those numbers once you have them by the greatest common factor. So in this case, you can pull a 50 out of each of those numbers and reduce them to a ratio of 3 to 2. The other way to do this, and you'd probably do that with a second version where I said the fast pump is 1.5 times as fast as the slow pump. There you might say fast is 1.5, slow is 1. Here I would recommend expanding the ratio by a factor of 2 to avoid having decimals. And you'd end up in the same place. You'd have a ratio of 3 to 2. The idea for ratios is you want to have the smallest integers possible to represent or to tell that story, to tell that ratio story. We don't want to have fractions in there because they're not necessary. We don't want to have big numbers in there because that's not convenient either. We like to have the smallest numbers possible. There's actually another reason why we should always use the smallest integers that fit the ratio, and that's because it's very helpful in situations where we have an integer constraint. When the ratio is comparing things that have to be integers, for example, books or people or dogs, you can't have 2.7 dogs, right? There's an integer constraint there. So whenever we have a ratio describing things that need to be integers, if we use the smallest integers that fit the ratio, we're guaranteed that the scale factor will also be an integer. And the reason for that, well, let's do this thought experiment. Imagine that the ratio of dogs to cats is 3 to 2. Is it possible that the scale factor is 1.5? You might say, well, for the cats, it is possible because there are 2 ratio units for the cats. So you could multiply that by 1.5 and you'd get 3 cats. So that's reasonable. But it wouldn't be reasonable for the dogs because you'd have 3 times 1.5 is 4.5, and now we have a fraction of a dog. So for this reason, as long as you reduce your numbers to the smallest integers that fit the ratio, you can rest assured that the scale factor is an integer. If your numbers are not fully reduced, let's say I had a ratio of 10 to 6 dogs to cats, or 10 dogs for every 6 cats, ratio of 10 to 6, well, now I might actually have a fractional scale factor. For example, half. Scale factor could be half, and the actual numbers of dogs and cats would then be 5 and 3. So this only works if we reduce the ratio all the way to the smallest integers that fit. And then if we have an integer constraint, if the story is about things that have to be whole numbers, we can rest assured that the scale factor is an integer. On the other hand, if the ratio is describing kilograms or feet or something else that doesn't have to be integers, then all bets are off. The scale factor could be any number. Let's take a look at one more example of how we can use ratios to our benefit. Let's say there's a retailer selling some product. Now, the retailer's cost for the product was 4/5 the retailer's profit for the product. We should immediately build a ratio for that. So we have the cost to the profit is a ratio of 4 to 5. And then we should pause and wonder, what inference can we make here? If you're a retailer and you know what something cost you, and you also know what your profit was, what can you infer? You'd be able to infer what you sold it for, because we know that the profit is the difference between your selling price and your cost. So if your cost was 4 and your profit was 5, you must have sold it for 9. And this isn't $9 or 9 of some other currency. This is all just a ratio. It's a simplified model of reality. But we have now this ratio of cost to profit to selling price is 4 to 5 to 9. And then we can say all sorts of interesting things. We can say the cost of the product for the retailer was 4/9 of the retailer's selling price. We could say that the selling price was 9/4 the cost. We could say the selling price was 9/5 the profit, and so on and so on. Well, I hope you can see now how valuable ratios can be on this test, and I look forward to seeing your comments below and your questions about this. If you like this approach, be sure to check out my book. It's all in there. What do you want me to talk about in my next video? Type it down in the comments below and maybe I'll make a video just for you. Make sure you're subscribed and click that little bell icon below so you don't miss any future videos. See you next time.